Welcome to lesson 5 of my refresher course for ordinary level. Today we're going to look at trigonometry. So we're going to go through some of the basics. We're going to go through some of the rules and have a look at some questions, maybe have a look at some exam questions at the end. Okay. So some warm-up questions to begin with. Which of the following statements are true? So I'll just give you a moment to look at them. Okay, so sine of 30 is equal to a half. So we have in this section here, we have a lot in the tables, and we can look here, sine of 30 is indeed equal to a half. Okay, so that one is correct. Cos of 45 is equal to 1 over root 2. And we don't even actually need the tables for that one. Let's just like go ahead and draw right angle triangle, right? There's a right angle. This is 45 degrees. That makes that one over here also 45 degrees. So this is an isosceles triangle. Let's just let that side be 1. Let's just let that side be equal to 1. What's this side here? Well, we can use Pythagoras. So this side, let's call it C. C squared is equal to 1 squared plus 1 squared. So C squared is equal to 2, which means that C is equal to the square root of 2. And then that means that cos of C is equal to 1, the adjacent, if we take this to be our angle. Our adjacent is 1 divided by the square root of 2. Okay, so cos of 45 is equal to 1 over the square root of 2. Tan of 60 is equal to 1. Let's have a look. In here, tan of 60 is equal to root 3. So that's not correct. That one was correct. This one is not correct. And then sine squared plus cos squared is equal to 1. Okay, so trigonometry, this is basically it means that if we're in we're looking at triangles and things like this that have missing sides and angles, we're going to be able to fill in those angles using trigonometry. So what trigonometry is, these ratios, let's have a look at a triangle here. So this side here in a right angle triangle is called the hypotenuse. It's the longest side in the triangle. And for this angle here, we have an opposite side, which is this one here. You call it the opposite, but it can be labeled with an A as well. And this is often labeled the hypotenuse H, or we can just, the labels sort of change from depending on, what page in the tables we're looking at or whatever, or where we are in the book. You have to be prepared for that. And this side here is the adjacent, or in this case here, it's given by B. So the hypotenuse is the longest side in the triangle. And if we think about what, so then we have the opposite, which is opposite from the angle. Now, if we were to do this angle here, then that would be the opposite, right? That would be the opposite there. And then, so we'd have to change these labels around, right? But the hypotenuse will always stay as the longest, and the hypotenuse is always opposite the right angle, okay? And what we then have is we have this SOH-CAH-TOA thing, right? Which is sine of the angle, sine of theta, is equal to the opposite of the hypotenuse. So this is, let's say, the angle here. And you see the way we're kind of doubling up here. So up here, I'm using theta, an opposite on hypotenuse. Here it's different. So this is, okay, this sort of happens. So let me in green, have this stuff here, right? Hypotenuse and adjacent, okay? So sine of theta is equal to the opposite over the hypotenuse. It's also equal to the, here it's equal to A over C, isn't it? A over C, that one. Cos of theta is equal to the adjacent of the hypotenuse. So that's also equal to B over C. And then tan of theta is equal to, where is it? Tan of theta is equal to the opposite over the adjacent, which is also equal to A over B. Now, what are these things? What are sine, cos, and tan? Well, we've got in our triangle, we obviously have 3 sides, and we can take ratios of those sides. And what do those ratios tell us? Well, like if we're in a triangle like this, which is like really, really not tall, right? Which is a really sort of slender triangle, right? Now this is, the hypotenuse is also going to be the longest side, right? This is, the sine is now going to be sine of this angle here, theta, is going to be small. Like it's going to be close to like 0, right? Or like maybe 0.1 or something like that, because that side is so much smaller than that side. When we make a fraction of it, when we take a ratio, then it's just going to be a small number, right? So what we're getting here from this is just basically like an indication of, are we talking about a triangle like this? Are we talking about a triangle like this, and so on? And sine, cos, and tan are just different ways of sort of describing the triangle, right? Now they have other uses, of course, but just in simple terms, they're just ratios, right? So they just tell us like if what kind of, like, depending on the formula, what kind of triangle, what kind of right angle triangle we're dealing with. Okay, so let's have a quick example. We're gonna um, we have we have the angle. So we have a question which is all in words, and it's just something to be kind of aware of in maths, that um, like I can kind of like I can probably describe something, like imagine I could sort of describe a place, and I could describe it with words, and regardless of how accurate you know my description is, it doesn't mean that that happens in your brain, right? So what we have like naturally is we have sort of intuition, which is good maybe with visual stuff, or maybe with other stuff. Like we have stuff that we're just naturally good at sort of understanding things with, and what we always want to be able to do is connect to that in whatever way is comfortable for us. So for me, like anytime I have a question like this, my first thing is to go ahead and just like draw a picture. Okay. So it's just sort of like, even looking at it, I'm just like, I have no idea what they're talking about. So what I'll do is I'll just take each of the components of this. So right angle, triangle. Okay. And then we have the hypotenuse is 10, and that's a right angle. And then the angle is 30. And we're looking for the opposite side. So we're looking for this side here, the opposite side. And we've been told to use sine. Okay. So for me now, this is sort of trivial. For this here, it's like, what are you talking about? But then now it's very straightforward. Okay. So I have SOH-CAH-TOA. So sine of the angle theta is equal to the opposite of the hypotenuse. And that means that sine of 30 is equal to the opposite, which we will just call, what we'll call it? We'll call it x, will we? X over 10. And so then we have 10 times sine 30 is equal to x. And then we have 10, x is equal to 10 times, and then sine of 30, if we go over to the table here, sine of 30 is equal to a half. So 10 times a half, okay? And that's equal to 5. Okay. So there we have like trigonometry in practice. We had some information about a triangle, and then you're like, then you're like, you can find. So we in general, like, we knew 3 things about the triangle. So in general, if you know 3 things about a triangle, you can get everything else, right? So you could use, if it's a right angle triangle, you can use Pythagoras, but when it's to do with angles and stuff, then you have to use these things here. So it's just a way to, in a triangle, there's 6 pieces of information, 3 sides, 3 angles, right? If you have 3 pieces of information, then you can get basically everything else most of the time, unless it's angle, 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 right? Then you can't do it. Or if it's side, side, angle, then it's ambiguous. There's 2 different triangles that fit, but just generally, like, if you have 3 pieces of information about a triangle, then you're going to be able to get everything else. Okay, great. So the next one, so using cosine. So again, a right angle triangle. Now let's just do it in a slightly different way this time. Let's make a right angle triangle, and let's say put the angle here. We're going to call that angle theta. And now we have that the hypotenuse is still the longest one. It's a right angle triangle. and the adjacent side is 5. And now we want cos theta. Now, what's different this time is that, you know, last time I put the right angle triangle with the pointy bit in towards the left, and then in the bottom right hand corner I had the right angle, and you know, that was the way I laid out my triangle that time. And actually, that's most of the time when I lay out triangles, I lay it out in that way. But then imagine something comes to me like this, and all of a sudden I'm like, oh, I'm not prepared for this sort of situation. Well, two options. We can turn this around like this. So instead of making a triangle like that, that's still 10. Now we put the theta down here, right? And now this is 5. So we could do that. But maybe better just to be able to say, well, look, what is cos theta? Cos theta is the adjacent over the hypotenuse. So let's just do that. Let's just be like robots, right? This is the angle. This is the adjacent. So it's like 5 over 13. See? And now we're done. So it's kind of like what I'm trying to do with when I emphasize these things in this way is to show you how something which is like seems to be very, very sort of straightforward is just like if you just sort of twist it a little bit, then all of a sudden it's like, oh, I don't know how to do it anymore. And it's just to kind of be able to kind of just get around these little kind of awkward ways in which things can be asked, right? When it seems like I don't know how to do this anymore, just to get past that little bump, basically. Okay, so now the question is to find tan theta. So again, we have a triangle. We have a right angle. We have an angle theta. We have an opposite side 7. We have a side here 24. Now, if you look at this here, this doesn't look like 7. This you know, they look like the same length, right? But we don't care. You know, like when we're doing a diagram like this, we're not measuring from it. We're just labeling, and this helps us to be able to put things into a formula. So tan theta is equal to the opposite over the adjacent, right? Now, the opposite here is opposite the angle is 7 over 24. Okay, then we're done. We can't go any further with that. Okay, so a triangle with hypotenuse 12 and an angle theta is equal to 60. So we have to find the opposite side. So this is the right angle. This is the hypotenuse is 12. This is the theta, which is 60 degrees. So I can write down 60. And we're looking for the opposite side here. Okay, so we're looking at this thing here. What do we have? We have an angle, we have a right angle, we have a hypotenuse. We're looking for this. So the formula that we need to use is sine. So you're going to have to like be able to decide which of the formulas from SOH-CAH-TOA to use. That's equal to the opposite over the hypotenuse. So in other words, sine of like 60 is equal to the opposite, which is, let's call it x, over the hypotenuse, which is 12. And this is going to be x is equal to 12 sine 60. And then we go to find out what sine 60 is. Sine 60 is equal to root 3 over 2. So that's 12 times root 3 over 2. And then we cancel that off. So it's going to be 12 over 2 is 6 root 3. Finish. Brilliant. Okay, so, and I think we can move on. Okay, so what we have something this time. Oh yeah, so this is this might actually be this one might actually be worthwhile. So we have a triangle. We have a theta. The adjacent side is 8. The hypotenuse is 10. And we're looking for sine of theta. And we know the sine theta from SOH-CAH-TOA is the opposite over the hypotenuse. This is the opposite. We don't have it. So what do we do? Well, we're going to have to get it. So how can we get it? Well, if you look now, our problem, so before we can do this sine theta problem, we have another problem, which is actually find the sides. And if we're given a right angle triangle and we're only concerned with sides, well, then we have a special formula we can use, which is Pythagoras. Okay. So this is what you would kind of call like a kind of like sort of a two-part type problem, right? It's like asking for sine theta, but before we can get that, we need to get this other thing first. So sometimes you kind of sort of think, well, that's not really fair. You've asked me a question, but there's actually a question in the question, right? But this is the way it is, right? So you could be asked something and you may be required to do sort of, it might be a way of asking you multiple questions in one, right? So the first one here is to say that this side we've called it x, using Pythagoras' theorem that 10 squared is equal to 8 squared plus what squared. So that's 100 is equal to 64 plus x squared. I bring the 64 across, 100 minus 64 is 36. 36 is equal to x squared. And this tells me that x is equal to 6. So this is 6. And that tells me that sine theta is equal to 6 over 10. Okay, so that's the opposite over the, so that's equal to like 3/5. That's sine of theta. Okay, so triangle with opposite side 5 and adjacent side 12. So it's the same deal this time. So we just draw that. Then the opposite side to the angle theta is 5 and the adjacent side is 12. Okay, and we're looking for cos of theta. So cos of theta is equal to the adjacent over the hypotenuse, but we don't have the hypotenuse. We don't have that. But we do have the fact that it's right angles. So that side x squared, I'm just calling it x now, no good reason. We could call it h, call it whatever we want. 12 squared. So this is like 25 plus 144. This is equal to 169. And then x then is equal to 13. So 13 squared is equal to 169. Why do I know that? The reason is 3, 4, 5 triangles, Pythagoras, it always works, also works for any multiple, 6, 8, 10. So I knew if this was 8 and this was the hypotenuse was 10, this one had to be 6. And the other kind of triangle is 5, 12, 13. These are called Pythagorean triads, right? And there's just a few of them that just always come up. So it's often either one or the other, but not always. Okay, so what we were doing so far was basically just finding cos theta, sine theta, or we've been finding the cos's and tans, which is just finding those ratios. But how do we now, if we have that sine of theta is equal to a half, how do we recover what the angle is from that? And if we have that cos of theta is equal to 0.6, how do we recover the angle from that? So what we're saying is that, you know, sine, cos, and tan, see, cos is this ratio, right? It gives you the ratio of B over C or something like that. And we know that, you know, if the angle was bigger or smaller, it would affect the ratio. Because just imagine, you know, just think of a crocodile open and spout or something, right? I know I'm using a silly example like that, but like it just, you know, you can kind of demystify this stuff, you know what I mean, just by connecting it to something a bit more kind of intuitive, right? So it's sort of like, you know, so cos is just but it is connected to the angle, right? So if we had a small angle, like a small angle, then cos would be, this is a small angle, would be this side over this side. Cos of that small angle, we'll call that angle A, is almost equal to 1 because that side is almost the same length as that side. But if we had a really big angle like this, then, and this is now our adjacent, and this is our hypotenuse, then cos of that angle is almost equal to 0 because, you know, it's the adjacent of the hypotenuse is so much longer than the adjacent, right? So we can see that the value of the ratio of value of cos or value of sine or something tells us something about the angle, but how do we actually get the angle is what I'm talking about. And we have another operation for that, which is just called the inverse sine or the inverse cos. Okay, so sine inverse and cos inverse of whatever that number was, a half. Okay, and 0.6. Okay. Okay, so let's have a look at this. So let's have a look at this. Sine of theta is equal to a half. And then I have like this thing, theta, it's almost like I divide across by it's almost as if I divide across. I don't, of course. But what do I do? Well, what I have in mathematics is I have inverse sort of operations. I have these, I could take 2, I could add 5, I get 7, but I want to get back to my 2. So I take the 7, now I subtract that thing that I added and I get back to the 2. I undid what I did. Same could be true for multiplication, division. Same for be like 2 to the power of x and then log of x to the base 2. So you have always operations and inverse operations. And basically sine has its inverse operation in inverse sine. And sine of theta produces a ratio. And inverse sine of that ratio gives us the angle again. So it's the same principle. Like every time, basically, anytime you've got a tool, you have to be able to have the inverse of whatever it was that that tool did. So if we have, a pencil, like, here's a pencil. At the end of the pencil, you got an eraser. So you can write with this end and you can rub it out on this end. If you have a hammer, so this is my crude drawing of a hammer, the end you've got like this claw thing so that you can bang the nail in, but you're like, I want to take it out. I've got the inverse tool on the other side. Or if you have a drill, an electronic drill, like here's my crude drawing of electronic drill, you have a button which makes it go clockwise, and then you go, oh no, I want to screw it back out, a button that makes it go anti-clockwise. So maths is no different. We're introducing all these number tools. Each of these number tools wants to have the ability to be able to undo what you just did, okay? And in the case of sine, cos, and tan, in the case of trigonometry, we have these things, which is inverse sine, inverse cos, inverse tan. These are used to produce the angles from the ratios. So this one here, sine of theta is like, let's get the ratio from the angle. Then the other one is like, let's get the angle from the ratio. Okay. So now it's say, given that the hypotenuse is 15 and the angle is equal to 40, find, okay, so I think I was just mentioning that there, okay? And now I'm back to, now this one here is to find the opposite and the adjacent, basically, right? So, okay, so I can basically say the hypotenuse, so I can draw my triangle, and the hypotenuse is 15. I'm just wondering how this now fits in to the rest. And this is my opposite. Let me call that O. We'll call that A. And now this means that, the sine of 40 is equal to O over 15. That tells us that the opposite O is equal to 15 times sine 40. And then the cos of 40 is equal to A over 15, which implies that A is equal to 15 times cos of 40. Okay. I hope you're okay with, like, sometimes calling this O, sometimes, like flipping around, maybe calling an X, these symbols that we use to, like, like to label the triangle sides. We're not sort of married to any of them. We're not fixed. It doesn't always have to be a particular way. Like they are just ways, they work for us, right? These labels are just something that we can, like, just come up with in the moment, use them for a second and just throw them away, right? We don't really need to be precious about them. You don't always have to give them the same name. So, okay. Okay, so now what happens a lot when you do these questions is you get like kind of word problems and stuff. And the problem, I guess, with word problems is that you have to be able to extract the sort of mathematical problem out of it. So basically, I want to be able to look at this question and draw a triangle and not think about, oh, is this 5 meter, ladder that's leaning against the wall is like dangerous, like, is this, is there, so like they'll give you these examples and it'll be like, oh, a ship is going over here, and you'll start thinking about ships and trees, and you have to basically. So what we're going to do is we're going to do a kind of a translation of the question away from the words into just like stuff that's more like mathy, right? So, okay, I'll draw a triangle. This is the thing that's leaning against the wall. The wall is going to be vertical, right? And the ground's going to be flat. So here's a right angle triangle. And it's the angle that is leaning against the wall with is 70. It doesn't matter if my diagram is accurate or not or whatever, just once it's not crazy, that doesn't throw me off. And what I'm looking for is how high it goes up the wall. I'm looking for that side there. I'm looking for the opposite. Why don't I call it X? Okay. So I have a triangle. I have this angle here. I'm looking for the opposite side, and I have the hypotenuse, the longest side. So what am I going to have to use? SOH-CAH-TOA. And the one that I want to use is sine. of theta is equal to the opposite over the hypotenuse. And now I have, like, that gives me that sine of 70 is equal to the opposite x over, 5. Right, so that means 5 is on, so now I'm going to take, multiply that 5 up, so that's x is equal to 5 sine 70. And what I'm also going to have to do with that, sorry, I shouldn't have put a box around that. So I'm going to have to multiply that out. I'm going to get a number, and I want to just at the end, whatever that number is, I'm going to call it meters, right? Because this was a question. So what I've done is I've had a kind of here's the real world, right? Here's the maths world, right, or whatever. So I've started off in the real world, I've jumped across over to the maths world. I've gone down answering the question, and at the very end, I have to jump back into the maths world again. So that might mean we just have to read the question. It might mean that we have to say that this is a number. The question might say, to the nearest meter, we just have to make that change in the end. So let's have a look. So this would be 3 marks out of 10, probably, for labeling the diagram or putting even just one label on the diagram. Like even that might be enough for 3 marks out of 10. They really give that 3 marks out of 10 away, like, pretty, it's not hard to get 3 marks out of 10. To get the 7 marks out of 10, we would have to get probably to here. The fully substituted formula, from which now is our launch pad for being able to finish off the question, or maybe even that line. So, okay. Right, so a kite string is 20 meters long. The angle with the ground is 30 degrees, and now find the height of the kite. Now, already your brain might kind of go, wait, no, there's something that I don't quite like about this. And if you've ever flown a kite, so here's you, and here's a kite up here in the air, you'll notice from your perspective that it's not a straight line. Okay, something like this. Now, if you don't believe it, just have a look. You'll notice that it always. So you'd be like, this is not like, if that's 20 meters long, well, then that's not. This would only apparently work if it was a straight line, right? Like with this here. So this is so we have this kind of discrepancy in this situation, right? And the reason why I'm bringing it up is not because we care about this, but because just when you're starting to answer the question, you can be like, there's something not quite right now. It can enter in a doubt into your mind, and then you're sort of like, should I be, do I need to consider this, or am I doing this right way? Or maybe I don't even like this question. Maybe I should just move on to the next one. And what I want to say about this is that this is kind of getting into a sort of an applied maths type of direction, right? Because we're starting to apply our mathematics in the real world. And for applied maths, we always have our approximations, right? So we'll have our first approximation, our second approximation, our third approximation, and so on. And like, let's say, for example, we were taking the first approximation of this kite situation here. We wouldn't worry about that bit. Like, we know that we're not quite right, but we're not expecting to be completely right. We just want to be mostly right. We want to be like 90% right, with that first approximation. Now, the second approximation might take into account that you have that kind of bend there in the thing. And I might say, you know what, the bend is always this much, right? But actually, you might be holding a kite going, when there's gusts of wind, sometimes it bends more, sometimes it bends less. And you get into all of these more and more complicated situations. And you get into a territory of like, well, do we actually care? Like, how accurate do we need to be? And this is something which is like, you see this in statistics and in probabilities later on, when you do these sort of statistical tests and stuff like this, you can say something with 95% certainty. I can say this is the kind of case, right? So you might, you might make some sort of like, they took a sample from the population. What they're able to do, say, with 95% certainty is that the mean of this group has changed or something like that. So what I'm saying is that as soon as we get into the applied maths type situation, we start to kind of depart from the sort of perfect triangles and the perfect stuff. However, we are actually dragging this problem you know, kicking and screaming into the maths world. And in the maths world, we got triangles. Okay, they've right angles. Enough. I don't care. Okay. So it's a long way of saying that we don't care. But the reason why I bring it up is because, you know, um, like there's sort of often there's like one way to be right. There's two ways to be right, maybe three ways to be right, three ways to do a problem, two ways, you know, there's a lot and a lot of different ways that you can have uncertainty and doubt. You know, maybe you're hungry. You know, like it can basically a feeling of uncertainty can kind of come from anywhere. So when it comes up, it's important to kind of be able to set it aside or handle it in some way so it doesn't stop you from tackling the problem. So long story short, we don't care about that. But it's a nice example to be able to bring it up, right? So okay, so we've got 30 degrees to ground. That certainly doesn't look like 30 degrees. We don't care. We're looking for the height, so we're looking for this side here. We'll call it h this time. And now we have that sine of 30 is equal to h over 20. We're now at the 7 out of 10 marks. H is equal to is equal to 20 times sine 30. And that's 20 times a half, and that's equal to 10. And then we're like, okay, yes, 10. Brilliant, fantastic. Next question. But we have to be like, wait. Was it correct? Let's go back to the question. And then it's like, oh, we were talking about meters, right? So 10 what? Is it 10 centimeters, 10 miles, right? We want to write the height. So the answer should be 10 meters. We would lose 1 mark if we finished here. We would lose 1 mark. It's not the end of the world to lose a mark, but you know, like don't lose a mark unnecessarily, let's say. Okay, so a ramp is 6 meters long and makes an angle 25 degrees with the ground. Find the height of the ramp. Um, so here we go. So here is the ramp. This is 25 degrees. It's 6 long, and we want to find the height of the ramp. So like this. So like this is our translation. This is how we're going from the world of words into the world of maths. And it's just like another, like if we think about this, so let's say a real world, right? And we move over to the maths world, right? The maths world is all of these qualities that the real world doesn't have. Like the maths world is all this stuff like logic, right? And you know, you can have this sort of ability to be able to say like A implies B implies C, and you know, use formulas and things like this. But the real world is always messier. It's always spongier. There's always like gray areas and everything like that, which is perfectly fine. But the discipline that we're learning in mathematics is to be able to take what we're considering and try and represent it as well as we can in a mathsy way, so we can do these mathsy things with it. And then at the end, we come back. Are we going to say we're right? We're going to say, well, look, this is what our model told us what's going to happen. So that could be like, you know, oh, the model says that the economy is going to grow. The model says that it's going to rain tomorrow. Like there's always models for every different mathematical models for all these different situations. And, you know, are they completely correct? Well, in the maths world, where they're done in the maths world, they're completely correct, right? But that doesn't mean that they're connected to reality, right? So what we're going to do is we're going to say a ramp is 6 meters long and makes an angle with 25 degrees. We want to represent the ramp with the ramp with this right angle triangle. But you know what? The ramp might be a bit bumpy, you know, and if it's 6 meters long, does that 6 meters that should be like this? Or, you know, you start to get into these awkwardness. But maths is like this kind of, you know, it's kind of, you know, for lack of a better word, it's kind of clean or something, right? But it's, you know, it's not, it's also, in a sense, it's sort of stuck in a corner, right? Like you can't describe everything, or it can actually only describe a limited amount in some ways, right? So, okay, so we want the height of the ramp. So we have that sine 25 is equal to h over 6. So that's h is equal to 6 times sine 25. Brilliant. Okay, move on. Now we have this other formula for the area of a triangle. So we have a few formulas for the area of a triangle. So if we have a triangle that's a right angle triangle, we have, you know, we can say, well, what's the height of the triangle and what's the base? So we can have the half the base by the height. But if we have a triangle that's not a right angle triangle, like this, we have a half the base by the perpendicular height. This is the perpendicular at this one. So you have to get this other side. Okay. Now, long story short, this triangle here, this b sine theta is the way that we actually kind of, the triangles that we're dealing with here in general will not be right angle triangles. So there might be something like this. And let's say this is C. This is A. This is B. Then a half A, B sine C. Now let's have a look at this here. Let's take B to be the base. So half the base. And then we're left over with this A sine C thing. What's that A sine C thing? Sine C is going to be the opposite over sine C. Let's take this now. Call that side there H. Now we mean, you see, now we don't mean H for hypotenuse, we mean H for height, right? So, you know, if we were married to only using H in a triangle to mean hypotenuse, we'd be a little bit. Here, A is not the adjacent or anything. It's, you always have to take your labels from the local situation you happen to be in, like where we are right now. H over A, see? So sine of C is the opposite over the hypotenuse. And you see the way that's now H over A, right? Because of the way that we've labeled things. It would normally be like the way the H would be on the bottom, right? So that can cause trouble. But you know what I mean? Like if you understand, it's not just SOH-CAH-TOA, it's not just these letters, right? What does it mean? It means the opposite side, which here happens to be, say, H, over the hypotenuse, which here happens to be A. So this is like A sine C is equal to that H. So this here is the H. So this is the perpendicular height. So this is the same as that formula there, just written in this one here. And if we go back to get this one here. Did I do it somewhere? No, I didn't. I'll bring it over here. I'll just draw it again. Let's do it on the same page. So now if I have a triangle like this, and let's put in angle A, side A, angle B, side B, angle C, side C. Okay, so let's write down a half AB sine C. That's A, B, and the angle in between. But we could do B, C, and the angle in between. Half BC sine A, or we could do AC sine B, a half AC sine B. They're all the same. They're all equivalent formulas, okay? It's just, you know, like we don't have to take the longest side to be our base. We could rotate a triangle around like this, and this might be our base, right? This could be our triangle like this. So now here could be our base, right? And where's our, this is our angle, okay? So that's our base, and this is our angle. Our perpendicular height is here, you see? So these different formulas just give you a different way to, you know, and we can set them all equal to each other. And then, and I'm actually, I have to look it up, but I'm not too sure if you do it on the ordinary level course. But essentially, if we go ahead and divide across by a half ABC, then we get the sine rule. Okay, so this is a way to derive then the sine rule. It just comes from the fact that we have three ways to write down the area of the same triangle using trigonometry. Okay, good. So take a few minutes to work out the following things. For the first one, I guess you'll need a calculator. For the second one, you need to draw a triangle. For the third one, we'll have to use Pythagoras and then use sine theta. And for the fourth one, we'll have to draw a picture of like a ramp or something like that. And then for the fourth one, then we'd have to draw a picture for the fourth one. Okay, so we'll have a look at the first one. So if sine theta is equal to sine inverse of 5/13, now we'll go across to a calculator. And when you do the calculator, I don't think we have the problem here. I think we're looking to find theta. So, if our calculator is set to radians, we'll get a measure in radians. If our calculator is set to degrees, we'll get an answer in degrees. You're going to have to look at the question to see if they'll say we want the answer in radians, we want the answer in degrees, okay? And just know how to switch the modes, okay? Because we now have two different ways of, oh yeah, so I don't think radian measure maybe doesn't come up, but it can happen that your calculator is set to the wrong mode. So just make sure it's in the right mode is what I'm saying. So I'll go over here and I'll say like 5 divided by 13. Oh, I think I need to use some other calculator to do that. Do I have another calculator? Okay, well I can say first sine. So it's equal to 22.6 degrees, okay? So inverse sine of 5/13 is 22.6 degrees. Okay, so the next one. Now, the next one, we have a few things. You know what? I'm going to draw a diagram just like quickly. And the diagram can always be done the same way. And we don't even really care if if it looks kind of accurate, right? So the opposite side is 12. The other one in here is 20, and we're looking for theta. So we have the opposite. So this is like SOH-CAH-TOA. So this is sine. So we have that sine of theta is equal to 12/20. That's the same as 6/10. That's the same as 0.6. So we have sine of theta is equal to 0.6. So theta is equal to sine inverse of 0.6. And then if I do that again, sine inverse of 0.6. Then I get 36.87 degrees, okay? 36.87 degrees. Okay, so right angle triangle, the adjacent is 4, the hypotenuse is 5. Find the sine of theta. So let's go ahead and draw this. And the adjacent of the angle theta is equal to 4. The hypotenuse is 5, and then this side here, the opposite side, let's call it x, is we don't know what it is. Now, if we want to work out sine of theta, we're going to need that opposite. We're going to need that x, okay? So what do we do? Well, we have to go back and get the x, okay? So how do we get the x? Well, we realize this is a right angle triangle, and now in order to get the x, we have to go that x squared plus 4 squared is equal to 5 squared. But you know what? This is a Pythagorean triad. This is a 3, 4, 5 triangle, so x is equal to 3. So now we can say it's 3/5, which is the same as 0.6. And then we just got that. Now sine inverse of 0.6 is going to be the same thing as we got last time, okay? So sine theta is equal to 0.6. That means that theta is equal to inverse sine of 0.6. Now, if you see the way I did that question, this is like a really good point here. It's just something that came up, and things come up when you do questions. So what did I do? So I just basically drew a triangle. That's a correct first step to make, perfectly valid. And then I went to do the triangle. I went to work out what I was asked for, right? So I'm sort of moving forwards in this direction. But then I went, oh, I don't actually have enough. I have two. Theta is an unknown. X is an unknown. I can't say what theta is because I don't know what X is. Now I have to go back. So you're doing the question and you're going down, going like step 1, step 2, step 3. Oh no, I have to go back to a step that was before step 1, and now this isn't continuing like if in a forwards direction. It's kind of going back. It's starting again. It's jumbled. It's all messy. It's all over the place. That's maths. So even though every example you see in the book is like pristine, like perfectly written and everything like that. And even though every conclusion that you make is just like perfect formal logic and all this, like it's sort of true and it's perfect and everything like that. It doesn't mean that the work is like that. It doesn't mean that the thought process is like that. And you wouldn't believe how many students lose sort of silly marks because they kind of don't want to write down work that's messy. But maths is messy. It's only after you have the whole, all the pages all over the table with all those scraps of solutions that you finally take one new sheet of paper and write down the perfect solution. But you weren't perfect in your mind the whole time. It's just something that people don't really get. They kind of think that they're wrong because they're messy, and it's just like, no, that's how you should be, right? You have to be thinking. That's really the kind of trick. So I just bring it up because things come up like that, and you're just like, you shouldn't lose. It's okay to lose marks when you don't know what to do, but losing marks when you know just for silly reasons is always a big shame. Okay, so find the height. We're going to call the height x. What do we call the height h? Just to screw with our heads a little bit. H is normally hypotenuse, so will this cause a problem? We'll use SOH-CAH-TOA. SOH-CAH-TOA, so now it means that sine is equal to the opposite over the hypotenuse. So sine of 15 is the opposite, which is h, over the hypotenuse, which is 10, okay? So remember, these symbols that we use, these labels that we put on diagrams, they work for us, okay? We don't have to, so we can name them whatever we want to and then throw it away afterwards, okay? And then the last one is work out the area of the triangle with sides 8, 6, and including an angle of 90. And this is another example that I also kind of like. So let's sort of draw this triangle. It's a right angle triangle, okay? It's got, what has it got? It's got sides, area of a triangle with sides 8, 6, and, okay, the question has been badly worded, but what I mean here is that this is 8 and 6. And there's an angle of 90. Now, we spent the previous slide basically kind of going through all of the different, this area of a triangle formula, and your mind will want to go straight to the relevant formula in the section, but actually this is just a half a base by the perpendicular height. This is just a half 8 by 6. 8 by 6. This is 24. Okay, so yeah, okay, so that's that. So let's quickly, if I can find, that's what I was looking for. I just want to find some exam questions. I didn't put them into the slide, so let me just go back to get some trigonometry questions, maybe just a couple. Like the point of the refresher course is not to, we're not doing exam questions, but nonetheless, I just want to kind of show you how how close what we're doing is to where you need to get to ultimately. So let's just take this first one. Maybe let's see how many parts there is. So here's a big long story about something or other that we're going to have to change into maths sort of stuff. So and then there's a second cable that's brought over. So I'm just going to add these three in. Okay, and then what you notice about these questions, by the way, this is 8A, and then there's part I, and I. So they'll all be connected together. then part B will be some other thing. Okay, so like it's important because if you don't get part I, then you can't get part I, and part. They're all connected together. But B is like a fresh start. Okay, so all right. So let me just put in the first one. So we have a fish shop has a vertical sign outside of its door. And in the diagram, the sign is represented by FH, that big line there. And FH is 3 meters, and a cable is tied to the top of the sign F, and it's secured to the point G on the horizontal ground. G is like 1.4 meters from the base of the sign H, as shown in the diagram below. And then we have to use Pythagoras' theorem to work out the length of the cable, which is like FG. Okay. So, if you're me, you're kind of, you start thinking, worrying it's going to fall on somebody or something like this. Is the cable strong enough? Like, what kind of sign is this? This is all what is making this question hard. It's basically just misdirection. Okay. So what we're going to do is we're going to ignore everything we can ignore in the story. We've got a right angle triangle. One side is 1.4. This side is 3. This is the hypotenuse. Let's call it H. And let's use Pythagoras. H squared is equal to 3 squared plus 1.4 squared. 9. And then let's go. This calculator can do it this time. 1.4 squared plus 9. So that's 1.96. So this ends up being like 11.55. And just as a 11.5510. So just as a kind of a rule of thumb, maybe carry 4 decimal places. So we'll carry 4 decimal places, and then at the end we'll figure out how many decimal places they wanted to. We will not round early. If you round early, you lose marks. It's a silly reason to lose marks. So H is that, and then we'll take H squared is that, and then we have to take the square root of this thing. So it's 3.39867. So it's 3.3987. 3.3987. 3.3987, and then double check. 3.3987. Is that right? Yeah. Okay. And then the next one. Show that the angle shows that the size of the angle FGH is correct to the nearest degree. Now, I don't know about you, but I've already forgotten my diagram. So let's go back, and we're going to draw out the triangle again. And I'm going to include a few more labels this time. So that's 3. This is like 1.4. This is 3.3987. 3.3987. Oh, I just lost a mark. Here, back here, H is equal to 3.3 meters. Why? Because they said correct to the nearest. Answer in meters, correct to 1 decimal place. So if we left it at that, you lose a mark, you get 9 marks out of 10. Here, now you get the full marks. So for the next one, it's always a little bit of a, sorry, it's not 3.3, it's 3.4, sorry. 3.4, right? So 3.4, and then let's just call, I think it's by now we can actually say, you might want to clear this up with your teacher. Like, I'm going to go in with 3.4 here because they've already told us to round it up. So I think now we can use 3.4. It's not, the question isn't about finding that 3.4, right? And also, G was the point on the ground. So that was the point G. This was H and this was F. So we're going to go GHF. So let me write them down. So this is GHF. So FGH, the way I look at that is it means, look at the middle one, the angle at G. That's how you read them real quick. There may be more than one angle at G, which if it's something more elaborate, but here it's clear. So we want to show that this is 65 degrees. So let's call that angle theta. And we can have whatever we like. Let's say, let's call it sine theta is equal to the opposite 3 over 3.4, which is equal to 3 over 3.4. Clear 3 divided by 3.4 is going to be 0.8824. So 0.8824. So generally, as I said, I just carry 4 decimal places because they never ask for more than 4 decimal places. And if we rounded earlier and we said, oh, this was 0.88, and then they were like, oh yeah, now give us your answer to 4 decimal places, then we actually lost marks. Okay, and that means that theta, to work out the angle, is sine inverse of 0.8824. So that's going to be, what's inverse sine of 0.8824? It's going to be 63.434 degrees. I've obviously made a mistake. See where I'm getting like theta is equal to 63 point. I'm going to leave that, not because I like it, but because even when we're doing it in this way, 4349, this is not 65. It's like nearly 2 degrees away. So we may have made a mistake somewhere when we did something. Where would it be though? Yeah, this doesn't seem right, does it? It's just this calculator that I'm using. What is, I'll do it over here. So 3 squared is 9. So what's that one? 1.4 should be squared. That's 1.96. And now we say, 9 plus 1.96, we end up getting 10.96. Okay, and then if we take the square root of that, we end up getting 3.3. So this should 3.31. So this should be 3.3. Sorry, I made a mistake there. So this should be 3.3. And then if we brought this over, then this would be 3 over 3.3, and then we would get 65, okay? Or something when we round it closest to the nearest degree. And then final, okay, and I think let's just leave it there. So that just gives us an indication of how they're applied there. So yeah, okay, so I'll send you a video of this later. And just want to say that I'm trying to start this grinds school basically, and reviews are super important. So I'm going to send a review in the email as well. And if you can, give me a good review or whatever, that would help a lot. And next week we're going to be doing more stuff. There's lots of space. So if you know anybody you think they're going to be interested, you can send them the links so they can check it out, or you can just, they can also just join in the meeting. It's no problem if you just send them the Zoom link or something like that. Yeah, so I'll see you next week and have a nice weekend.